Greetings. My name is Lonely Noveas. The topic I will deal with what is about high efficiency MOSFET Transformerless Inverter for non-solar and micro-inverter application. Definition. This definition based in glass low control level metal or series semiconductor field affect transition MOSFET basis transformerless photovoltaic PV inverters can achieve high capacity by using lattice per new MOSFET. In any case, these MOSFET basic inverter topologies encounter the superimposition of no less than one of these drawbacks. Topic one. El abstract, the MOSFET basic inverter topologies, el circuit diagram, existing system, proposed system, the total and software used. Applications in electronics. The MOSFET leak down younger from body diode pivot recovery is thinking that conduction events are a result of more device or low magnetic usage. The PWM, the PWM and the proposed transformer is inverted has no the time necessary use basic PWM regulation for use and you say unlimited high recurring CN user a two hardware fitting double the hardware model house been planned crack and three into around hence non-insular microinverted application. Topic one. The topic one PV. The PV MOSFET transformerless inverter is shown for the PV microinverter application. The pulse width change PWM direction and circuit undertaken rule are then described. The ordinary mode and differential mode the voltage show is then display and consider from circuit structure. The topic two. The block diagram, the phase one to stage non-insular PV microinverter, el PV panel, el de DC the non-insular high STU converter DC-DC, DC link y del proportional transformer inverter DC AC, el break. And topic 3.
Welcome to Pattern Solutions. Today we are going to see transformerless single-phase inverter. This is the driver transformer. This driver transformer is supplied to the driver board, and this is the power transformer. This is the power supply to the main circuit, and also connected to the big controller input voltage, and this big controller is used for generate the PWM signals, and the PWM signals is connected to the driver board inputs, and the driver board is used for period impulse of 15th pin. 16th pin. 17th pin. 18th pin. 23 pin. 24. And I will check the output voltage. This is the output voltage of transformerless single-phase inverter. Thanks for watching this video.
The pros and cons. The pros and cons.
And today we're inside Cree's Power Applications Lab, where a lot of the magic happens, where we use our C2M technology and our latest silicon carbide Schottky diodes to shrink the size of power electronic systems. And there's no better system to show this advantage of silicon carbide than in DC to DC converters. And I got a couple of examples to show you here today. First up is a 10 kilowatt boost converter that we designed for the PV market. So these boost converters are used in PV string inverters. And what we wanted to do was build a reference design with silicon first using IGBTs. These are high voltage inputs. So using 1200 volt silicon IGBTs, and then compare that to a solution if we had used silicon carbide devices instead. So if we look at this block diagram of a 10 kilowatt system, what you're looking at is a two-phase interleaved boost converter connected to a inverter stage. So each phase leg is switching at 20 kilohertz in case of silicon, and then they're switching, and with silicon carbide, they're switching at 100 kilohertz. So if you look at the performance of this system and compare it against these 5 parameters, if you look at the losses, the weight, volume, cost, and temperature of the system, if the blue line represents the silicon solution, then the green represents the silicon carbide solution. And what you notice is that we reduce the filtration unit. And what I want you to note is the boost inductor, the size of the boost inductor. This is a 20 kilohertz boost inductor that we have to use with the IGBT solution. It weighs 2.4 kilos, it's pretty heavy, gives you a good workout. But when you go to a 100 kilohertz switching frequency, you end up with a boost inductor that looks something like this, about the size of a small donut. It weighs 0.4 kilos. So going 5x in switching frequency actually reduced the weight of the boost inductor by more than 5x. And that's really where most of the cost, weight, and size savings comes from. Interleaved phase legs. Each phase leg is switching at 75 kilohertz. And what you'd notice is that the entire system, the whole 50 kilowatt system, fits on a single board. The board by itself weighs 7 kilos, and that includes the magnetics, the heat sinks, the power switching devices, the gate drivers. We have little daughter boards that are the gate drives. We also have little daughter boards for the control card. This is an analog controller. Our purpose was to show the power density and the power to weight ratio rather than advanced control schemes. So if we look at this system, we have the 2 inputs for the PV panels. We have a EMI filter, a common mode choke for the filtering, and then we have our 4 boost inductors, and then these are the heat sinks with the silicon carbide MOSFETs. Here we actually have 2 of the devices running in parallel to form the boost switch, and we also have 2 Schottky diodes, silicon carbide Schottky diodes, in parallel in the boost circuit. So we have 4 phase legs, and then this is the output. So you supply about 400 volts on the input side, and it boosts it up to about 850 volts on the output. This is air cooled. We have a couple of fans to cool it, and we actually sell this as an evaluation kit online, so customers can try it out and see the results for themselves. Here is a 50 kVA spring inverter. Now let me tell you about the size of this box. This box is roughly the size of a 27 kVA spring inverter that's available today in the market. We've taken that same size box and we've crammed 50 kilowatts into it. And this is only possible if you're using silicon carbide devices. So looking at this box, we start out at the input. This is where the PV panels connect to our boost converter, which I showed you earlier, 50 kilowatt boost board. It then has a DC link. We are actually using film capacitors in our DC link. There's 3.5 millifarads of upper and lower film capacitance in here. If we had used electrolytic capacitors, it would have been certainly a lot smaller, would have weighed less, and would end up with a lower profile. But we use film capacitors for reliability reasons, because it's a trend in the industry to use film capacitors to improve reliability of the whole system. We also have a auxiliary power supply. It's also using a silicon carbide MOSFET device. So our auxiliary power supply, boost converter, DC link, and then this is our inverter stage, where each bolt represents a T-type inverter phase link. This also uses our 25 milliohm MOSFET, C2M MOSFETs.
The process stage of the are low power, the metal oxides, semiconductor field effects, transition MOSFET. The basic transformerless photovoltaic PV inverters can achieve high efficiency by using LED supercussion MOSFET. The cons is a cons this MOSFET basis inverted topologize suffer from one or more of these drawbacks. The drawbacks resolve MOSFET, the future to the virtual recovery of the body diode, the increasing conduction losses due to more device or low utilization of magnetism. In conclusion, MOSFET Transformerless Inverter with a novel model. The basic stage leg, which achieved high ability by up to super intelligence, the MOSFET and synthesize. The limited anger from the MOSFET stay legs by part the MOSFET stay lay like we use to the day inductor and limiting the DGT from MOSFET, the body of the switch recovery. Thank you.